For this video, we're going to do a quick review of phasors before re-examining transmission lines through this new lens. So recall from our previous discussion, we can define the solution of the transmission line equation as some function of t minus z over vp if it's traveling in the forward positive z direction, or the backward propagating wave, let's just call it b. T minus z over vp. In the case of phasors, let's assume that they're sinusoids of frequency omega. So our forward propagating wave, which is a function of z and t, we're going to specify, instead of this general form, we're going to specify it as an amplitude cosine of omega and then t minus z over vp. Or let's just distribute this omega in. Vf of zt is going to be equal to the amplitude cosine of omega t minus beta z for a wave going in the positive z direction, where beta is going to be defined as omega over vp. Now, one of the things that I'll point out is that, well, let's look at the backward propagating wave. So a wave going in the negative z direction, in this case, following that same rule. Oh, sorry, this should be a plus here. Following that same logic and form will look like this: omega t plus beta z, where again, beta is omega over vp. So one of the key things to note is that, first of all, for if it's going in the plus z direction, that means that t and z have different signs. Just like how what we had described before when we were looking at these in generic form. And the second thing is beta, which we've defined as omega over vp. And if you plug in expressions for vp, one of the ways that I commonly remember it is 2 pi over lambda. And this expression has units of, if you look at this, of 1 over meter. Another way to look at this is radians per meter. So this is the spatial equivalent. What omega is to time, beta is to space. So if I were to look at this as a function of time, and the wave goes like this, and I were to take a freeze frame, the amount of time it takes to do one cycle is associated with radians, is associated with omega, if I convert omega from cycles to radians. Similarly, beta is the same thing from a spatial domain. So if I take a snapshot of my wave as a function of distance, and I look at how long it takes to do a cycle, the amount of radians per meter is what this beta means. So again, I think it's important to remember, whatever omega is to time, beta is to space. Now what we're going to show is that in phasor form, so this is what we'll call the instantaneous form. The phasor form, we're going to show that you can take this instantaneous form, and first of all, we can rewrite it like this. So Vf is going to be the real part. If we apply Euler's rule, V naught e to the j omega t, e to the minus j beta z. And the backward propagating wave is going to be the real part of V naught e to the j omega t, e to the plus j beta z. And so in particular, we note that we have this e to the j omega t in common. So really, what we want to just keep track of is this term and this term. So these two together, we call the complex amplitude. So this is like if you were just looking at e cosine omega t, if you extract this phase portion outwards, the time-independent phase portion outwards, you end up getting a complex number, and we'll call that the complex amplitude. So it's like amplitude, except it includes the phase information. This real part, taking the real part of this e to the j omega t, we can just ignore that for the time being. Let's just keep track of the complex amplitude in our calculation. So for phasor calculations, all we're going to do is we're going to ignore the whole process of taking the real part and having the e to the j omega t. We're just going to focus on the part that actually changes for a fixed frequency, namely this complex amplitude. So we're going to, for forward propagating wave, we're just going to set it as a function of z, and we're just going to keep track of v naught e to the minus j beta z. Similarly, the phasor form for a wave propagating in the negative z direction will be v naught e to the plus j beta z. And the idea is that we extract this part, do our calculations, and then when we're all done, we slap the e to the j omega t back on, take the real part, and then we now have our instantaneous form. So we'll go back and forth between these two forms. Let's take a look at what that means graphically. So recall from Euler's rule, if we have in the real and complex plane, if we have a vector in this real and imaginary plane of length a, angle theta, Euler's rule states that we can write this as e to the j theta, and that is going to be equal to a cosine theta plus j sine of theta. And of course, j refers to the square root of -1, and we use that as electrical engineers, with apologies to basically the rest of the world, which uses the much more sensible letter I, which in electrical engineering is unfortunately reserved for a bunch of other quantities as well. It also makes us more of an exclusive club. So when you look at this, you can also graphically see that the real part of a e to j theta is going to be the projection onto the real axis, a cosine theta, and the imaginary part of a e to the j theta is going to be equal to a sine theta. So what are we actually doing when we're doing phasor analysis? Well, what we're actually saying is, if we take a look at the complex amplitude, let's just take a look at a generic v naught e to the j beta z. So let's just say v naught e to the j beta z looks like that, where this is length v naught, and this angle is going to be beta z. That is basically where this vector sits at t equals 0. So that is what the situation looks like at t equals 0. And then once you start the clock and let t evolve from 0 to positive infinity, you're multiplying an e to the j omega t to the angle, meaning that it will start rotating in the counterclockwise direction at a rate of omega radians per second. So when we say phasor analysis, what we're doing is we're saying, let's just keep track of this vector here. Let's just keep track of the initial condition at t equals 0. We're going to strip out the information about the frequency. We're just going to keep that in the back of our head, what frequency we're worried about. We're going to see what the system does to this vector at t equals 0. And then when we want the instantaneous form, when we want to be able to determine what the field looks like at any point in time, all we have to do is just start rotating it at omega t and add that factor in. So phasor analysis is basically saying, let's plot it on the real and complex plane and only worry about the initial position. And because we're just throwing away, we're not throwing away, we're just putting aside information that we know, namely the fact that we're looking at the projection on the real axis, and also that we are going to be rotating it at frequency omega t. So this combined with Fourier analysis is really powerful, because we can decompose any periodic signal into its constituent set of frequencies, and then for each of these frequencies we'll have a complex amplitude, and when we pass through a system we just have to see how this complex amplitude changes, and then we'll be able to describe the system. And if we want to describe the system for all time, we just perform the operation and convert it back to instantaneous form. So let's wrap up by just outlining the steps of how to go from one form to another. Let's clean up a small corner of this board. So when you're doing the analysis, first of all, step 1, let's just start with the instantaneous form. So start with the instantaneous form here. We have it in a nice sinusoid. So first of all, we want to rewrite in complex form. So rewrite in complex form. So in the case of, we'll just focus on a positive going wave, it would be the real part of, and I'm going to do some rearranging, but it's going to be V naught e to the minus j beta z e to the j omega t. Next up, we extract, so step 2, we extract the phasor, or the complex amplitude. So in this case, VF, so over here this is a function of z and t. Now it's just going to be a function of z, because we're extracting the complex amplitude, which is not dependent on t, or another way to look at it is we can just set t equal to 0. But our phasor form of this signal is going to be V naught e to the minus j beta z. So step 3, I'll just simplify as we're going to perform analysis. So we're going to do a bunch of stuff that we're going to learn in subsequent sections and chapters. So where this is the stuff that we'll get to later, but the point is we get this to the phasor form, and then next, once we have our final answer, we convert back to instantaneous form. To the instantaneous form. And there's 2 steps involved. So 4-1, the first part is you multiply by e to the j omega t. So we're going to basically redo everything that we did here. So first of all, by extracting this, what I meant was we took out the e to the j omega t, so now we're going to multiply it back. And then step 2 is we're going to take the real part. And then you're done. So again, as a quick recap, the whole point of phasors is if you know that you're working with a sinusoid, a particular frequency, all you have to keep track of for your analysis really is the complex amplitude. Or another way to look at it, it's where the vector is at t equals 0. So we extract that complex amplitude, and that is what we refer to when we say phasor. Then we do our analysis looking only at this phasor, and then once we're all done, we're going to have some kind of output, some kind of calculated value that's also going to be just a function of z because it's also a phasor. So to get it into a function of t and z, we convert to what we call the instantaneous form, and that is just undoing the steps here. We multiply by e to the j omega t, and we take the real part, and that is how you get 2 phasors and back.